All right, 75 kilograms skier traveling at a constant velocity on a 10-degree slope. Question is identify the direction and magnitude of all the forces acting on the skier. So first step here, right, in any of these balanced force problems is going to be to draw a free body diagram. So acting on our skier, we're going to have some force of gravity, right, straight down towards the center of the earth. The slope, the hill, the ground is going to exert a force on the skier perpendicular to the slope, right? So it's going to be not exactly on the same line as gravity, right? Which is going to complicate things a little bit for us. And then, right, the skier is moving along the slope, and I haven't said anything about it being frictionless, so it's safe to assume that there's a little bit of kinetic friction that's acting against the direction of motion of the skier, right? And since it's indicated that the skier is traveling down the slope, friction is going to be up the slope. So just a rough sketch here of our free body diagram. Do my best to keep these as much as we can, right? We're going to have this here. Go ahead and put some arrowheads indicating the direction of these forces. Here we have a normal force, right, acting on the skier perpendicular from the ground. Here, kinetic friction, and then our force of gravity. And you'll remember, right, our next step here is to either rotate our axis plane, right, so that at least two of the forces are no longer in 3-dimension, right? So you can either kind of tilt your head to the side, right, so that your axis, this is now x and this is y, right? Or you can shift the whole free body diagram so that it follows our traditional coordinate plane, right, of this whole thing. And I've usually shown you this way here, but I want to, in an extra help session, a couple people were using sort of shifting the whole free body diagram. So I want to do that for you guys now and see if it helps anyone who's kind of stuck on this. So if you shift the whole free body diagram, right, it's going to look something like this. Go ahead and throw my labels back in there. A few arrows. Right, now Fn is straight up, right, in the y direction. Friction force is horizontal, and it's our gravitational force that is slightly askew in 2 dimensions. Right, this is different than, previously I was showing you, all right, now this is our y-axis, right, and this is our x. You can do it either way. It just depends on what feels better on your brain, right? It's a little bit of mental gymnastics to do this, and whichever one is easier for you is fine by me. So now that we've switched our, sort of rotated our free body diagram, we can divide FG into components to create situation-specific equivalencies, right? So if we go ahead and draw a right angle triangle here for this, right, this is going to be FGY, and then this little short guy here, I may not have space to draw a little arrow, is going to be FGX. I'll blow this up in a second so that we can really see what's going on. And we know since the skier is traveling at a constant velocity, the forces must be balanced in all directions, right? Right, he's not floating up off the snow, he's not crashing through the ground, and he's not accelerating in any direction, right? So there's no F net. And based on that, we can determine our situation-specific equations, SSEs, right? Fn must equal FGY, right? Vertically, these two values these magnitudes must be equal so that they cancel each other. Make my y look less like an x. There we go. And horizontally, the kinetic friction force must be equivalent to the x component of gravity, this one here. They should cancel each other. Okay, their magnitudes should be the same. So we have these situation-specific equations, and now we want to apply our general equations, right, to see if there's anything we can solve for. And one general equation that's going to come in handy most often, right, is Fg equals mg, right? So we can solve for Fg here. This is going to be 75 kilograms times 9.8 meters per second. And this equals 735 newtons. So that is the magnitude of Fg. And if we blow up our right angle triangle here, right, let's make this a little bigger. That's Fg, there's Fgy. So basically what I've done here is I've taken this little triangle and I've made it bigger just for the sake of showing what's going on. I'll go ahead and put some labels on here so that's clearer. Fg, go in that direction. Here's Fgy, and Fgx. This angle in here, right, is always going to equal the slope of the incline, right? You remember we did some geometry legwork to prove this, right? If that boggles your brain, right, all you have to do is accept that these are always equal, right? And since we have this angle and we have the magnitude of the hypotenuse, right? Remember we just solved for this being 735 newtons. We can solve for these two values using trig, right? Fgy, let's see, I'll do this down here so that I have more room. Right, Fgy is adjacent to the angle. So we could use cosine, adjacent over hypotenuse. Fgy is going to equal the cosine of 10 times Fg, right, 375 newtons. That value is 723.8 newtons. And Fgx, right, is going to be opposite, so it's going to be sine of 10 degrees times 735 newtons equals 127.6 newtons. Cool. So we've just done a little bit of trig here to figure out these components of the gravitational force. And actually in doing that, if we look back at our situational equations, we've solved for the normal force and the friction force, right? Because they are equivalent to those components. So we've solved the question, right? We can go back up to our free body diagram, which indicates the direction of the forces. I'm actually just going to redraw it down here for us. Right, there's gravity, normal force, and friction force. I'm going to indicate the directions with some arrowheads on my vectors. And indicate the magnitude. That's going to be my answer, right? Fg we said was 735 newtons. The kinetic friction we said was 127.6 newtons. And our Fn, normal force, was 723.8 newtons. Right? So this is going to be my answer right here, this whole free body diagram. The reason that this needs to be my answer, and I can't just throw the numbers out there, is because of the wording of the question, right? Remember, the question asked for you to specify the magnitude and direction of all the forces acting on the skier, right? If you just give me the numbers, you've given me the magnitude but not the direction. By putting them in the free body diagram, right, the vectors indicate direction of these forces. All right? For now, I just want you to be putting in vectors and not worrying about signs. We'll worry about signs next semester. All right?